Hello friends, our video today is about graphing antiderivatives. And what I'd like to start out with is, suppose I have a derivative function, and let's just make this thing relatively simple here. I'll call this f prime of t because it is a derivative, and let's say that it starts out at -1 and goes for a couple units from 0 to 2 at -1. And then let's suppose that we start increasing and then continue like that. So that would be 3 and then 4 and then 5. And let's stop this thing at 6. Now, this is a derivative, isn't it? And so what I'm going to do is I'm going to try to take this information that we have and construct the parent function f of x. We have to keep in mind that these are slopes. But unfortunately, what I don't know is I don't know exactly where to start, because I could have an infinite number of offshifts of f of x, up or down, and that wouldn't change the slopes at all. And so I'm going to have some seed value. And the seed that I'm going to start out with is, let's suppose that f of 1 equals 0. So let's begin to graph together here. And I think f of 1 equals 0 is a great place to get started. Now, if I look here, what does this tell me? Well, this area between 1 and 2 tells me how much f changed. I could write that with the fundamental theorem. I could say the integral from 1 to 2 of f prime of t dt is equal to f of 2 minus f of 1, or the change in f from 2 to 1. But as much as I like that, we could also say that, you know what, the slopes this entire time were -1. And what is that space there? That area is a -1. And so we should go down 1 unit, and now we're going to be at 2, -1. Okay, let's think about what happened here. What happened here? Well, we went down 1 unit again, but I was at 0. So I went down to get to 0, and so the output here should be 0, 1. It corresponds to a 1 unit drop, another 1 unit drop, and now we're going to start increasing again. Now, mind you, these are slopes. And so at 3, what's the slope going to be? Well, it looks like it's going to be 0. And so that means that my parent function will have a horizontal line there, or a horizontal tangent line. What was the slope at 4? Well, 1. And so now the slope will be 1 here. So let's start looking. How much did the function change in going from 2 to 3? Well, this area here is -1/2. And so the function decreased by 1/2 a unit, bringing us to 3, -1.5. We then increased by how much? This area is 1/2, and so we went up by 1/2 a unit. And mind you, the slope there was what? The slope was 1. And so I'm dashing that slope in the same way that I did right there. Now, let's think of one last idea, that this is a linear function. What did I have to take the derivative of to get a linear? And that was a quadratic. So the antiderivative of a linear is going to be a quadratic. So I'm going to connect these 3 points, and that's going to be 4, -1 with a quadratic function. Finally, what's happening from 4 to 5? Well, the slope was 1, but Furthermore, the area here is 1, and so it increased by 1 unit, and at 5, we are at 0. And once again, from 5 to 6, we have a 1, and at 6, we'll be 1 unit higher. Okay, so let's have a recap here. When the derivative is constant, we have this linear function. When the derivative is constant, we have a linear function. And when the derivative was increasing, we were concave up over that entire span. Let's try it again with a different derivative and a different function. This time, let's use g. And I'm going to give a little bit different here for g. Let's have this point be -2, -2. Let's have 0, 2 happen there. Let's go like so. To, let's call that point 1, 2. And then let's go down. And then let's just stay horizontal. So we'll have the point here at 2, 0, and let's say 3, 0. Let's call this g prime of t, the slopes of g of t, which I'm going to graph right here. Now, similarly, if I have a parent function, this thing can have any upshift or downshift, and so I need some starting point. And so let's say that g of 0 equals -1. Let's call it right there, and let's start building. So we were at 0, -1, and let's start moving forward here. The slope at that point was what? Well, the output was 2, so the slope is going to be 2. And how long did it have that constant slope? Looks like 1 whole unit. So the width was 1, the height was 2, and the area of that piece is 2. So in going from 0, I'm going to be going up 2 units. And our new point is 1, 1. Keep in mind, once again, that this is a constant, and the antiderivative of a constant is a linear function. I mean, the slope here is 2. Okay, let's go again. Now, in going from this point, 1, 2 to 2, 0, what's the area there? Well, we could say that the height was 2, the width was 1, and the area would be 1/2 the base times the height. And so we should have an area of 1 there, shouldn't we? That tells me that my function should increase by 1 unit. So we were at 1, 1. Now we should be at 2, 2. But how did we get there? And what I want you to keep in mind is that these are slopes. At 1, the slope was 2, right here. Yeah, and that slope is going to continue, but at 2, what was the slope? Oh, we're all the way down to 0, and so I'm going to dash in that horizontal tangent line. The derivative was decreasing, which meant our parent function is going to be concave down. There we have it. The final thing that happens from 2 to 3 is nothing. The slope here is 0. And so from 2 to 3, our function is going to be a dead-on constant. Okay, let's build this part now. And what I'm going to do is I'm going to first notice that here we have the point -2, 2. -2, -2, and we had the point 0, 2. So what's that point at 1 going to be? Well, it has to be 1, 0, and that should help us, or sorry, negative 1, 0, and that should help us think about what the area of this spot is. Well, the height was 2, the width here was 1, and so we can have 1/2 times 2 times 1, and so that gave us a height of 1. Now, when the slopes are positive, my function did what? It increased. And so in going from -1 to 0, we increased by 1 unit. And so my new output value is going to be -1, -2. I want to reiterate that the slopes here were positive, the area here is positive, and so our function increased in going over. But because I was at -1, I need to say, okay, I increased from -1 from -1 to 0, and so I had to be below that value. How much below -1? Well, 1 unit. Now, the slope here was 0. The slope there was 2, and so I can connect these beautifully. But once again, this is a linear function, and the antiderivative of linear should be quadratic. Let's keep going. Now we have a -1, and we can just see that by symmetry, yes? So in going from -2 to -1, these are x values, the function decreased by 1 unit. So we went down by 1 unit to get to there, which means we had to be 1 unit higher. And the output was -2, -1. Let's check again. The slope here was -2. So we're going to have that nice negative slope. The slope at 0, or at -1 was 0, and we see that linear function, and I can really transition that into a quadratic. In our next problem, we're going to start doing some old exam questions to begin to play with the idea of graphing antiderivatives.